Griffiths Electrodynamics problem 3.9. So first we're going to go over example 3.2, and then we'll dive into problem 3.9. So this is an image charge problem. Basically what we have to do is picture a conducting sphere. It's actually a spherical shell, and because it's a conductor, it's also an equipotential. So what we're doing here is we are placing an image charge a distance b from the center of this spherical shell, and we want to know how big, what magnitude must this charge have, and what distance must it be from the center of the spherical shell in order to exactly recreate the electrostatic potential that exists outside of this conducting sphere. So if we look, we go through example 3.2, and we find out that the magnitude of the charge, which we'll call Q prime, is our image charge, is this minus r, where r is the radius of the spherical shell, divided by a. A is the distance out from the center to the original charge Q, and then multiplied by the magnitude of the charge Q. So notice that it's opposite in sign, and then let's see, because a is larger than r, it's also smaller than the magnitude of Q. So in reality, what's happening is, as we bring in this, let's just say this is a positive charge Q. As we bring in this positive charge Q, it's attracting negative charges, which are free to move around inside the conducting shell, and so you get sort of a net negative charge in the direction towards this positive charge that we're bringing in. So this charge that's moving around inside the shell, even though the sphere is still an equipotential, it does affect the potential out here. So this image charge is going to recreate that potential out here. Alright, so let's just double check, and just for fun, let's just make sure that this is still an equipotential if we satisfy these conditions right here. Okay, so, and then by the way, this would also work for cylindrical symmetry if we bring in a line charge here, and we have an image line charge inside this infinite hollow cylinder. Right? The geometry is all the same. So I'm just going to pick a point out here, which, if I draw a little displacement out here from the center of the shell. Alright, so I'll just use Cartesian coordinates. So this is just going to be a point x, y. And let's just look at the potential. So we have our 1 over 4 pi epsilon naught. We have now we're just going to add the potential due to both of these charges. Let's add our original charge first. So up top we have the magnitude of the charge itself, and then we've got what we want to do is find the distance from this charge out to our field point out here. So in this case, we get an x, or we'll have this a minus the x. So if I want to, so there's x, out here is a, we're taking the distance, the difference, and we want the magnitude, so this will be, anyway, essentially absolute value. We're just using Pythagorean theorem. And then a y squared is the y distance, and this is all to the 1/2 power, or square root. Now we want to do the same for this image charge. So let's go ahead and plug this. Well, okay, let's do the other side first. So here's our q prime, and then we've got, what do we have? We have this x minus b squared plus, and then y squared again, all under a square root. I should have been more consistent with the 1/2 and the square root. All right. So now let's plug in these values here, and what we should get is that we'll get 0 all the way around, because in example 3.2, this is a grounded sphere. Okay, so we have our 1/4 pi epsilon naught. Q, we have an a minus x squared plus y squared, 1/2. Okay, now we're plugging in what we get over here. So we have a minus r over a q, and downstairs we are looking here, we've got an x minus this b here, which is an r squared over a squared plus y squared. This time I'll be consistent and have a 1/2 out here. So far what we've done is really general, right? So this could describe the potential due to these two charges, the image charge and the actual charge, anywhere. But we know, of course, we're comparing it to this real situation of the spherical shell, that if, this potential is only good out here on the outside. But what we wanted to show was that we do, in fact, for points on this sphere, we get an equipotential. So in this case, we would get a potential of 0 all the way around the sphere. And hopefully this is still worth the time it takes to do this. So for the condition of being on the sphere, then we know that x squared plus y squared is equal to r squared. So big R being the radius of this shell again. So this is just the equation of a circle, right? Which, if we rotate our sphere until these points are all coplanar, then yeah, that's what we're dealing with. It's just a circle. So what I'm going to do is go ahead and substitute this in for y squared. So and I hope this is actually helpful. I don't know. You can fast forward if you're not getting anything out of this. Okay, so for y squared, we have an r squared minus an x squared. So that's what I'm going to put in for this y squared right here. And of course this is all to the 1/2. Now we have a minus, we have an r over a q, and then x minus r squared over a, and then this is all squared, plus, and then an r squared minus an x squared to the 1/2. So we just have to show that this is actually equal to this, and that will show that on the surface of our spherical shell, we have a potential of 0 all the way around. It's an equipotential. and therefore we're still we still have a good analogy with a conductor when we're using these image charges. All right, so let's go ahead and let's just write out this little a squared or a minus x squared thing. So I'm just going to write the inside, I'm just going to write the guts of this denominator down here. So a squared minus 2ax plus x squared plus r squared minus x squared. So we see that these two x squareds are going to go away. So the guts of this denominator here are r squared minus 2ax plus a squared. Okay, so now let's do sort of the same thing with this. The guts of this denominator here, we get an x squared minus 2xr squared over a plus r to the fourth over a squared, and then plus this r squared minus x squared. And this x squared is also going to go away. So what do we need to factor out in order to clean this up? Well, our goal is to have it look like this. So if well, obviously it has to cancel with this if what we're saying here is true. Oh, and by the way, I guess I factored out this q. So let's go ahead and factor out an r over a. What can we lose, right? But this is under a square root, so let's factor out an r squared over a squared. Okay, so this first term we get a minus 2x and an a. So we factored out this r squared, factor out an a squared instead of an a, we have to put an a up on top. Plus, left over we will have an r squared. So we factored out this r squared over a squared. That's all we have left on this one. And then we just have this r squared that we factor out, and then we'll multiply, all that's left is an a squared. So, and because this is all under the square root, when we can take this term out of the square root, and the squares will go away because we take the square root, and then this will divide out with that. And what do we have here? The guts of these two denominators match up. So that was probably not worth it, right? But we get a 1 over this r squared minus 2ax plus a squared. We're just beating this dead horse pretty good. All right, this obviously cancels with that. Gives us a 0. So it's just saying that when this condition is met right here, meaning all the way around this circle, when we rotate it around the symmetry axis, gives us the whole sphere. When that condition is met, as long as we're on the sphere, then the potential is equal to 0. So it's an equipotential. So anyway, there's that example 3.2. Now we can finally get to problem 3.9, what we were going to do in the beginning. All right. Hopefully you skipped all that if you weren't interested. Let me go ahead and write this. Okay. So that way, if you're fast forwarding through the video, maybe this will tell you when to hit play again. Alright. So, with the addition of a second image charge, the same basic model will handle the case of a sphere at any potential v naught relative to infinity. So, really, this is a short, simple problem. We just had to go and make it all complicated by going through that example. So what we saw before is that the image charge that we have already, q prime, sets this whole sphere out at radius big R to 0. And furthermore, we know with electrostatics being a linear theory and everything, we can use the principle of superposition. That means if we want to have, we can just add these potentials all together. So if we want the potential out here to be 0, or sorry, to be v naught, and it's 0 already with these two charges, then we just add a charge that will make the potential v naught out here. So symmetry makes this nice and obvious, right? We need to put a charge right here in the center, right? Because that will change the potential up from 0 equally in all directions. So let's find out what that charge has to be. So if we want v at, using a spherical coordinate, this radius big R, if we want this condition to be met, then we need to, we'll have a 1 over 4 pi epsilon naught, and then we'll have some charge, which we'll just call q prime prime. You know, if we're adding another image charge, q prime prime, and then the distance out to where v naught is, which is the surface of this cylinder, of this sphere, sorry, is big R. Alright, so we can just solve this equation right here, since v naught is just given to us, that's what we're controlling. We can just solve for this q prime prime. So I'm just multiplying everything through. So we have a 4 pi epsilon naught up on top now, we have a big R, and we have a v naught. So that will tell us what q prime prime needs to be in order to get a potential, now instead of 0, a potential of v naught out here at the surface of this spherical shell. Alright, well, so now what we want to do is find the force of attraction between a point charge q and a neutral conducting sphere. Alright, so if you look up at equation 3.18, it'll give you the previous case and you know what we would get for the force of attraction. Let's do it for a neutral conducting sphere. So again, we have the same conditions are going to apply. Right, because this sphere is still an equipotential. But now we're going to be adding this, we're going to be adding another charge q prime prime here in the middle, which will, what we have to do is cancel out the charge q prime here on the inside. So what we're doing is making this conducting sphere electrically neutral. So right now, to an outside observer, you know, using Gauss's law or whatever, you can tell how much charge is enclosed in this in this spherical shell, and it's Q prime. So we need to add another Q prime here at the very center, which, since it's at the center, the sphere stays an equipotential, but now Q prime prime will be equal and opposite to Q prime, so that the sphere as a whole is electrically neutral. So let me just write that out real quick. Q prime prime is equal to minus Q prime, and Q prime is equal to this. So minus Q prime is just R over A of Q. What is the force between the two charges? That's just by Coulomb's law. We'll just go with magnitude. What we're looking for is the force of attraction, right? So let's just go ahead and put our 4 pi epsilon naught out front. So Coulomb's law will need the product of the magnitudes of both charges and then divided by the square of the distance, and that's for each pair of charges. So let's just write this out to start with. So to get the force, let's just start with Q prime. We have Q multiplied by Q prime, okay, and then the distance between Q and Q prime, which is A minus B, and the distance is squared as well. All right. Okay, so now let's add in the force due to the second one. So we have the charge that we're using as a test charge, and then we have our second charge. Let me write that in here. Q prime prime is right here at the center. And now we need the square of the distance between them. In that case, it's just A. All right. So now what we have to do is just plug in for B, Q prime, and Q prime prime. I'm going to factor out this Q. We can go ahead and put in Q prime. So let's just factor out the other Q while we're at it and make this a Q squared. So what do we have left? We had a minus R A over A, right? And then an A minus B, and B is this R squared over A. Q prime prime is just equal to this. Okay, so again we factored out this Q already, so we have an R over A. And then downstairs we just still have an A squared. Alright, let's just double check real quick and make sure we don't need to, because we may need to put in a minus sign or something. We're looking for the force of attraction, and we know that Q prime is negative or of opposite charge to this charge we're bringing in. So this term should be positive, right? Because we're looking, again, the problem asks for the force of attraction. So let me write attraction. Okay, and then we'll put in a minus sign to make sure these terms have the right sign. Okay, and I'm going to add that in this way. I'll distribute that minus sign through here. All right, let's factor out a, so we have a q squared over 4 pi epsilon naught. Let's factor out this r over a real quick. Just to clean things up. And then, let's see, how should we do this? Alright, so we're going to factor out this 1 over a. So we have an a squared here minus an r squared. And then this 1 over a has this, it's within this, squared power here. So we get a 1 over a squared, that factors out, and then let's flip that up to the top, so we just have an a squared here on top. Okay, so now we factor this out, so we have a minus 1 over a squared. So let's find a common denominator and send this problem home. 4 pi epsilon naught, we have our r over a. And now, so I need an a to the 4th over a squared minus r squared minus a squared minus r squared over this a squared. Lots of a squared. Okay. I really hope I did this right. Okay. Normal chunk out front, r over a. And now we've got, let's go ahead and write out the top. So we have an a to the 4th, and then we'll have a minus. Here we have an a to the 4th minus 2a squared r squared plus r to the 4th all over a squared minus r squared. Quantity squared down here. So this and this will cancel, and I'm going to bring this minus sign inside, so we have a plus here and a minus here. So q squared over 4 pi epsilon naught r over a. We have, let's factor out another r squared and this a squared down here. And there's an, yeah, so we'll have a factor. Let's just r squared over a squared. Write this out. And what do we have left? We have a 2a squared minus, there's an r squared left right here. We are factored out this a squared, so we just have an a squared minus r squared. Quantity squared down here on the bottom. Okay. We'll do one more line and just combine these two terms together real quick. Q squared over 4 pi epsilon naught. Then we have an r cubed, a cubed, and then a 2a squared minus big R squared, a squared minus big R squared, quantity squared. And this is our answer. I don't remember what it was. We were finding the force of attraction. All right, and this was for a neutral conducting spherical shell. So A is larger than R, right? So these are all positive quantities here. Force of attraction is equal to this. It's positive. So that just means if I find myself a conducting spherical shell, and I find myself a little test charge and bring it in, the charge is going to be attracted to the shell. Why is that? Well, the charge is going to pull negative charges inside the conductor towards it. So if this is a positive charge, then the negative charges will be drawn towards it. And then there will be more negative charges that are closer to this charge than positive. And because the force between charges goes as 1 over the square of the distance between them, then the negative charges that are closer to this charge will attract it more than the positive charges will repel it. So there will be a net attraction. And we see as A gets smaller, just looking at this, you see as A gets smaller, this force of attraction will grow. So the charge will, the closer and closer it gets, the more and more it's attracted, and it's just sucked in and drawn to the and just sticks to the conductor, joins the charges here in the conductor. Of course, then, if we pull in a positive charge, then this sphere is no longer electrically neutral, and if we bring in another positive charge, then it will be, there will be a repulsion to deal with as well as the effect that we've described for a neutral shell. So, anyway, I think we've probably beat this problem to death, and then some.